So now let's talk about change of bases in per unit analysis. Let me tell you why we need to change the base in per unit analysis at all. So let me give you an example. So let's say we have a system, a generator, then we have a transformer. Now let me do it in this form. So I have my transformer, my generator. So this is the way that power engineers usually use the single line diagram. And we have, let's say, a transmission line. Then let's say we have another transformer, and then this is my load. Okay, so let's say the nameplate for this generator is the base of the generator. So generators usually have their own impedances as well. So let me put them into this figure also. So I have my generator, and then this is the basically XD, which is the direct axis reactance of my generator. When we get to basically the electric machines chapter, we will talk about this in more detail. But let's say we have this. This is my generator. This is my transformer number 1. So this is my G, this is T1. This is my transmission line and line. And this is my transformer 2. Okay, so let's see in the nameplate of each of these components in the system what we have. So let's say XD is equal to 0.2 per unit on the base of this base of my generator is, let's say, 50 MVA, and V base of my generator, let's say, is equal to 14 kilovolts. Okay, so when we say a per unit value, we must always determine what are the bases that we use to find that per unit value. So on the nameplate of a device, when we say that the reactance is this much in per unit, we should also look at the rating of that device, and we should know that that per unit value has been expressed based on those basically bases. So this 0.2 has been found out based on SVG and VBG. All right, same thing for transformer number 1. Let's say the transformer number 1, X T1 is equal to, let's say, 0.05 on the base of transformer number 1, which is 60 MVA, and the voltage base of transformer number 1. So V base 1 or V base high of T1 over V base low, V base low for T1 over V base high of T1 is equal to, let's say, 13.8 over 500. So this means that on the low voltage side of my transformer, on this side, my base is at 13.8, and on this side, the base of voltage is 500 kV. Okay. Now, let's say that I have my transmission line. My transmission line X and it's modeled with its X, but its X line is 0. For example, 0.04. But in terms of where the base is, S base of my line is, let's say, 100 MVA, and V base of my line is, let's say, equal to 500 kV. And finally, we reach T2. So T2, its nameplate is XT2 is 0.08, for example, and S base of T2 is also 100 MVA, and my V base on the high voltage side of T2 over V base over low voltage, V base of low voltage of T2 is equal to 500 over 20 kilovolts. Okay, so so far, is it clear what I'm doing? I'm just saying that we have a problem like this. These are a bunch of devices, and the impedance values of these devices have been given to us in per unit, but based on their own bases. And now we want to do the analysis in the system. If you want to do the per unit analysis in the system, you have to put or transfer everything, all of the impedances, to a common, consistent base. All right. So let's say we wanted to do the per unit analysis in the system. Didn't we have to find out how many areas of voltage we have or how many voltage levels we have before we do the per unit analysis? So let me just remove these because it might be confusing. So from here to here, everything should be on the same voltage level. The transformer on its low voltage side, this is an LV to HV transformer. Like this is LV, this is HV. And here we have HV, LV. So everything should be on the same base of voltage. Now for your line, as long as you are on the high voltage side of your transformer number 1, go to the high voltage side of transformer number 2, this whole area has its own voltage base. Okay? And then finally, this is zone 3 or area number 3 in terms of voltage. Okay, this is the common practice that we would do for doing per-unitization, right? Nothing new. Now, my question is, go ahead and find out or try to analyze this system based on per unit. So what is the rule? We should have a common base for the whole system, right? So that common base, what do you want it to be? Let's choose it 100 MVA, okay? Which is the same base as the base of this line as well as this transformer. So because it's similar to the bases of 2 of my components, probably when I have my base in this value, I would need to do less calculations on these 2 devices, okay? But again, this space is completely arbitrary. It's in our hands, whatever you want to choose. Now, we said 3 zones of voltage. So let's say V base 1, V base 2, and V base 3. Let me choose V base 1. So let me start the problem from area 1 and assume V base 1. This is another rule for per-unitization. I can choose whatever value I want on one side and then move around to the rest of the system and determine the bases to the rest of the system based on the turns ratios of the transformers. So I choose V base 1. What do you want it to be? I think it makes sense to make it 13.8 kV. Yeah, you're right. So yeah, I'll choose it to be 13.8. Okay, so based on this, V base 2 doesn't need any calculations. It would be just equal to what? 500 kilovolts. And V base 3 would be just equal to what? 20 kilovolts. Yeah, we're right. If I had chosen V base 1, for example, equal to 14 kilovolts as the base of the generator, then I would have a harder time because I should have calculated V base 2 and V base 3 based on the turns ratios of the transformers. Good. Okay, now that I have chosen my bases, then I should basically change the per unit values of the impedances of my devices, and change them to this consistent, basically base system, if that makes sense. So this means that I should convert this 0.2 per unit to a common base. I should convert 0.05 per unit to this common base, and so on and so forth. So this is the reason that we need to do change of base, because we've been given like many different types of devices by many different manufacturers, and these are not necessarily on a common base. These are on their own basis. So in order to basically solve the problem, we have to take everything to a common base. So here is the rule for changing the base. So if you have basically a new base system versus an old base system, then R, or impedance in the new base system, this is how it changes. Let me go back to, so you can use this Z base mu over Z base, sorry, not Z base, Z per unit. Z per unit, the new value over Z per unit, the old value, would be the same as S base mu over S base old times V base old over V base mu squared. So this means that if you change the base of voltage to be 2 times, if you change the base of power to be 2 times more, your per unit value will become 2 times more. But for the voltages, that's the other way around, plus there is a square factor involved. So this means that if you increase your voltage base to 2 times more, then the per unit impedance becomes 4 times smaller. So look at this. This is the rule that we use basically for per-unitization. Now, it can be proven very easily. I don't want to go through that proof, but you can do it on your own, or you can Google that to find out why this is the case. But it's really, really easy. Remember that these are per unit values in the old and new base system. And to basically find a new per unit value, we have to use the old and new base voltages. And these are the physical bases. These are in like MVA, KVA, and things like that. V bases are in kilovolt, volt, and things like that. But these are the per unit values in the new and old system. Okay? Now, with that said, I want you to spend a few minutes and give me basically these per unit values in the new base. So I call them XT new, XT1 new, X line new, as well as XT2 new. So there are 4 values here that I want you to convert to the new common base. All right. So we chose the new bases, the new base values, which was the S base equal to 100 MVA, V base 1, 13.8, V base 2, 500 kilovolts, V base 3, 20 kilovolts. This was what we did. Now, using this formulation, okay, still talking about that. So XT new over XT old would be the same as S base new over S base old. But what is S base new? S base is the new base of the system, the common base, which we chose it to be 100, right? And what is S base old? S base old is the one on the nameplate of my generator, which is 50. So here is 100 over 50. Now, we have to put V base old. So what is V base old here in the nameplate? 14. And V base new is obviously V base 1. We have to choose the V base which is on the side of that device, which would be V base 1 in this case. So this gives us whatever value. XD was 0.2. So this can give us, if I do it in MATLAB, this will give me 2 times 14 over 13.8 squared times 0.2. That becomes 0.4117. That's or as a result, XD new becomes 0.4117. Now, let's go to the next device. So we're talking about transformer 1. So the old value is 0.05. The old base is 60 MVA. What is the old voltage base? The old voltage base would be the one on the low side or the one on the high side, whichever you want to choose. So it's either 13.8 or 500. So I'm going to just explain it here. So XT1 new over XT1 old, which is 0.05, is the same as the new base for power, which is 100, over the old base of power, which was 60 times. We need to have the V base old. Now, if you choose the V base old on the low voltage side, you have to choose V base 1 as the new base of voltage. If you choose a V base high on transformer 1 at 500, then you have to choose basically V base 2. So you have to be consistent, if that makes sense. So this is equal to, the old value is 13.8 over 13.8 squared. We haven't changed the base of voltage, if you noted that. Or it could be 500 over 500. So simply speaking, since we have not changed the base of voltage, therefore XT1 new becomes 0.05 times 100 over 60, which is 0.083. Okay. Now, can you tell me for the X line and XT2 right away, what are the basically new values of per unit reactance? Yeah, that's correct. I mean, we can use the same formula, but is there really a need to do that? Have you changed any bases for these two, for X line and XT2? Have you changed any bases with respect to the common base that we're considering?
No.
No. So they remain unchanged. X line and XT2 remain unchanged. The new values. So X line new would be the same as X line old, and XT2 new would be the same as XT2. Okay. Let's go to another example. This figure is showing a simple single-phase system with 3 voltage levels. The rated values and other system parameters and knowns are shown in green. We want to use the per unit analysis with arbitrary rates to find VS and use the physical units directly to find VS. So in other words, we want to do this problem in 2 different methods. Method 1 is through per unitization. Method 2 is directly using the physical units. Okay, so make sure that you can read basically these correctly. So this is a 10 volt over 20 volts. So it takes the voltage, raises the voltage from 10 volt level to 20 volt level. This is the turns ratio of the first transformer. RT1, so this is called T1, is 0.1 ohms. Okay, so whenever you talk about the ohm value in the transformer, you should always mention to which side that ohm value has been referred to. So this 0.1 ohm has been referred to the 20 volt base side. R line is 0.2 ohms. And then we have for the transformer number 2, 20 volt over 10 volt, that's the turns ratio. And now we have RT2, the resistance in this transformer is RT2.10 in 10 volt base. So it's based on or referred to the 10 volt side. And then V load is 10 volts, P load is 20 watts. So looks like we're not considering any reactances. So my transformers just have impedance values, resistance values. My line is only resistive. This is just a simple way or problem to show you how to do the per unit calculation. And I did not involve the reactances just to make calculations simpler, so that you could do it manually easily. Okay. Any questions on this so far? All right. So we wanted to do that using per unit analysis. So in part 1, we assume an arbitrary power base of 10 watts and V base 1 to be 10 volts. So I chose my V base 1 here to be 10 volts, and I chose the power base of my system to be equal to 10 watts. So this is basically what we need to do for periodization of a system. We choose a common base for power and the base of voltage in one side of the system. Once you choose the V base on one side of the system to be this much, then the rest of the side's base voltages would be found. So based on this, since the turns ratio of this transformer is 10 volts to 20 volts, this means that V base for this VB2 should be 20 volts, and then VB3 should be what? 10 volts. So very, very simply done. We don't have to do the calculations really, because you're not changing the bases with respect to the rated values. So when bases are not changing with respect to the rated values in your transformer or in other device, then this means that there would be not a lot of calculations in terms of changing the base voltages and so on. Now, Z base 1 would be V base 1 squared over P base, which is 10 volts. V base 2 becomes V base 2 squared over P base, which is 40 ohms. And Z base 3 becomes V base 3 squared over P base, which is 10 ohms. As a result, the per unit impedances will be, so you have per unit impedances or resistances in this case. Each of them has to be found based on dividing RT1 or their value divided by their base impedances. So I'm finding RT1 in per unit by dividing 0.1 or the physical value over Z base 2. Why do I need to find that based on Z base 2? Correct, because the 0.1 ohm value has been expressed on the 20 volt base, basically, which is belonging to area 2, which has a base voltage of VB2. So therefore, RT1 in per unit would be found based on 0.1 divided by ZB2. And our line in per unit is 0.2, its actual value over Z base 2. And RT2 in per unit would be found based on its physical value over Z base 3 again. So why Z base 3? That's because RT2 has been expressed on the 10 volt base side. Okay? Now, once you find out the impedances, then everything would be converted into per unit. So PL in per unit would be found from the 20 watt over its base. So the power would be 2 per unit. VL in per unit would be found by dividing 10 volts over the base of voltage, which is V base 3, which is 10 volts. So therefore, VL in per unit becomes 1. So we have 3 resistances in per unit that we need to count for. Using these two values, VL and PL, you can find out the current or IPU. And then you can basically write up a KVL to find out VS in per unit. Very easily done. And then once you find VS in per unit, VS in the physical unit would be found by multiplying the per unit value by the base value of the voltage on its side, which is 10 point, which becomes 10.35. Now, the other basically method is to use the physical units directly to find VS. Okay. So this requires a lot of basically voltage and current conversions. So I can still start the problem from where I have the information. So since I have PL and VL, I can find out the current here, the load current. So the load current would be power over voltage. So PL, correct, PL over VL. So the actual values. What is PL? 2, 20. And what is VL? That's 10, which becomes 2 amps. So 2 amps we get in here. Now, on the other side of the transformer, how much would be the current? So on the other side, on this side, the current would be half of it, or 1 amp. But there is a voltage drop because of this RT2. How do you find a voltage drop? And to what side has been that voltage drop referred to? So it means that 0.1 times 2 0.1 times 2 becomes 0.2 volts. And this has been referred to which side? To 10 volt side. As a result, while I'm moving from here towards the source, and since ultimately I need to find out the voltage of the source, I need to transfer this voltage to the 20 volt side. Does that make sense? So referred to 20 volt side, how much would that voltage drop be? Let me call it delta V associated with transformer number 2. So it becomes delta V2. So see, what I'm trying to do is that I need to add 3 voltage drops associated with this transformer, this line, and this transformer. But they all need to have been ultimately need to have been referred to this side, or the 10 volt side. Does that make sense? So because I want to find out, do you agree that if you call delta V1 plus delta V2 plus delta V3 under 10 volts, so this is how I'm trying to 10 volt side, 10 volt side, 10 volt side, plus VL referred to the 10 volt side, that should become VS. Do you agree with this? So delta V1 is the voltage drop associated with this transformer. Delta V2 is the voltage drop associated with this line. And delta V3 is the voltage drop associated with the second transformer. And I have to add them all to V load to find out VS. That's KVL, right? So, can you tell me what is V load? V load referred to the 10 volt side. How much is it? V load referred to the 10 volt side. It is already in the 10 volt side, right? So it is 10 volts. Then, how much is the voltage drop here referred to the 10 volt side?
0.2.
0.2, exactly. 0.2. Now, how much will be the voltage drop here referred to the 10 volt side? So this is 0.2 referred to the 20 volt side, right? You have to multiply 0.2 times, what is the current on the 20 volt side?
1 amp.
The current on the 20 volt side is 1 amp, correct. That becomes 0.2, but this is referred to where? 20 volts. Now, if you refer it to 10 volts, you should take half of it, right? So you put half of it. In other words, delta V2 referred to the 10 volt side is 0.2 divided by 2, which is 0.1. Okay, same current is going to this side, and on the 20 volt base, is 0.1 ohms. So 0.1 ohms times the current on the 20 volt side, becomes 0.1 times what? Times 1 amp, which becomes 0.1 volts. This is referred to the 20 volt side, but I want to refer it to the 10 volt side, so I need to take half of it. So 0.05, I should put it there. So go ahead and add these two together. That becomes 10.35 volts, which is the same answer that we got in here using the per unit. But see, it was a lot confusing, wasn't it? So that's one of the advantages of per unit, because you have to make, once you do everything in per unit, you're sure that you're just using the numbers in per unit. Do the KVL, KCL, easily find out the answers, and then return everything back to the physical units. But when you're doing the actual units, you have to always be concerned about transforming the voltages and currents correctly to the other side. And that is sometimes confusing, and you can and you will make a lot of mistakes.